We all know that supernova explosions are some of the most spectacular fireworks that cosmic nature has to offer. A single such explosion contains an enormous amount of energy. A single supernova can cover an entire galaxy for weeks or even months, amounting to at least a few 100 billion stars per second. But all that is a diamond compared to the most mysterious and powerful object in the universe, the quasar. In 1960, astronomers working with the Palomar Observatory's 5-meter telescope detected a remarkable, barely visible star in the constellation Virgo. But it was this spark that ignited the flame. 3 years later, the same object had a very large redshift, indicating that it was very far away from us and very bright. According to calculations, the distance to the target is 620 megaparsecs, and it is moving at 44,000 kilometers per second. An ordinary star cannot be seen here, and because of its size, it did not look like a galaxy. At the same time, this object was detected by a powerful radio source, and the name Quasar was born. Before the astonished eyes of astrophysicists appeared a completely unusual object, shining in the visible radio spectrum of electromagnetic waves. So far, more than 20,000 quasars have been discovered, some of which are clearly visible in the X-ray and radio spectrum. Moscow astronomers Sharov and Efremov decided to find out how the brightness of the first discovered quasar changed in the past. It turned out that the object changed its brightness several times, increasing almost twice and sometimes 3 or 4 times. Experts now realize the importance of this observation. But a few decades ago, scientists were convinced that the radiation from the galactic nuclei of the optical region comes exclusively from the billions of stars there. And even if a few thousand of them for some reason will go out, from the Earth it will not be noticeable. This means, the researchers concluded, that most of the stars in the galactic core should erupt synchronously. Although, of course, no conductor can lead such an orchestra. So it was precisely because of its sheer incomprehensibility that this discovery never attracted enough attention. Further observations showed that the change in intensity of radiation, with a period of several months for quasars, is a common phenomenon, and the size of the region of radiation does not exceed the distance that light travels for these very few months, and in order that changes in all points of the region occurred synchronously. It is necessary that the information about the beginning of the change had time to reach all points. It is clear that the matter of the quasar emits light not on command, and by virtue of the processes occurring on it. But the fact of synchrony, that is, simultaneity, changes in the conditions and magnitude of radiation indicates the compactness of this quasi-stellar object. The cross-section of most quasars apparently does not exceed 1 light-year, which is 100,000 times smaller than the size of the galaxy. But this does not prevent them sometimes shine like 100 galaxies. As always, immediately after the discovery of quasars began to introduce new physical laws, although at first it was not even clear what matter they consist of. Thus, the emission spectrum of quasars was unusual. However, a little time has passed, and the chemical composition of the radiation regions of quasars was determined by the spectral lines of known chemical elements. Hydrogen and helium in quasars are identical to Earth's. Only their emission spectrum appeared to be strongly shifted to the red side because of their high escape velocity. According to today's accepted model, a quasar is a supermassive black hole that pulls in the surrounding matter. As they approach a black hole, charged particles accelerate, collide, and this results in the strong emission of light. If the black hole has a powerful magnetic field, it additionally twists the falling particles and collects them in thin beams, jets, flying away from the poles. Under the action of powerful gravitational forces created by the black hole, the matter rushes to the center, but moves not along the radius, but along the narrowing circles, spirals. At the same time, the law of conservation of momentum forces the rotating particles to move faster and faster as they approach the center of the black hole, simultaneously collecting them in the accretion disk. Thus, the whole structure of a quasar is a bit like Saturn with its rings. In the accretion disk, particle velocities are very high, and their collisions produce electromagnetic radiation of other wavelengths, in addition to energetic photons and X-rays. At collisions, energy and speed of circular motion of particles decrease. They slowly approach the black hole and are absorbed by it. Another part of the charged particles is directed by the magnetic field to the poles of the black hole and flies away from there at a tremendous speed. This is how the jets observed by scientists are formed, the length of which is 1,000,000 light-years. Particles in the stream collide with interstellar gas and emit radio waves. The temperature in the center of the disk is relatively low, reaching 100,000 degrees Kelvin. This region emits X-rays. A little farther from the center, however, the temperature is slightly lower, around 50,000 degrees Kelvin, where ultraviolet light is emitted. Approaching the boundary of the accretion plate, the temperature drops, and in this region is the emission of increasingly long electromagnetic waves up to the infrared range. There is another version, according to which quasars are the first young galaxies, and the process of their formation we observe until now. However, there is an intermediate form, although it would be more correct to say a combined version of the hypothesis that the quasar is a black hole absorbing the matter of the forming galaxy. In general, almost all scientists agree that quasars and black holes are closely related. But this is only based on the fact that, other than a black hole, no other object known to us can give that much energy to a quasar. My personal opinion is that a quasar is dependent on a black hole, but to claim that they are one and the same is too presumptuous. Most likely, a quasar can be called a product of strong gravitational energy released from a black hole. The quasar is powered by the black hole. It is like its engine. But we're not saying that an electric current and a light bulb are the same thing, are we? Moreover, in early 2019, the brightest quasar so far was discovered. It is located 12.8 billion light-years away from us. Its brightness is comparable to that of 600 trillion suns. But nothing lasts forever, and when the matter near the center of the black hole shrinks, the glow disappears. There comes a point when the black hole absorbs most of the surrounding space, after which the radiation almost stops, and the black hole becomes a dim object. It's waiting to be discovered. As soon as new matter appears in the vicinity, for example, when two galaxies collide, the black hole glows with renewed vigor and greedily absorbs stars and particles from the surrounding interstellar gas. Modern technology already allows us to distinguish around distant quasars separate stellar structures, which are a breeding ground for insatiable black holes. In our time, however, when galaxy collisions are rare, quasars cannot occur. Almost all observed quasars are at a very significant distance, which means that the light coming from them was emitted a long time ago, back in the days when the first galaxies were born. That is why quasars are sometimes called the dinosaurs of the universe, alluding not only to their extremely venerable age, but also to the fact that they are, figuratively speaking, extinct. Such powerful sources of radiant energy as quasars are dangerous neighbors, so we, Earthlings, can only rejoice in the fact that they are not nearby. But why are quasars present in some galaxies and not in others? Let's remember that the light from the quasars we observe has been traveling for billions of years. This means that quasars appear to Earthmen in its original form, as they were billions of years ago, and by today probably already lost their former power. Consequently, these galaxies near quasars see much fainter light sources. But if the universe is homogeneous, the same should be true for our galaxy. And here we still need to look closer at the nearest cosmic structures to us to find objects that look like cooled quasars, a kind of ghost quasars. It turns out that such objects do exist. Quasars were born almost at the same time as the universe, about 13 billion years ago. Moreover, not only are they very far away from our galaxy, according to Hubble's law of expansion, the farther away an object is from us, the faster it moves away. The distance between us continues to grow. Thus, the most distant quasars fly away from us at just 5% of the speed of light. To release a huge amount of energy, a black hole absorbs a mass equal to the mass of the Earth every second. About 200 solar masses are absorbed every year. This process cannot continue indefinitely. Once the surrounding matter dries up, the quasar either stops working or begins to emit relatively weakly. Scientists are almost certain that black holes play an important role in the formation of galaxies. The discovery of quasars strongly influenced the whole cosmology and gave rise to many new models of the origin and evolution of the universe. Quasars, by the way, in many ways contradict the Big Bang theory, which, I want to remind you, is generally accepted in the scientific world. But we'll talk about that in our next videos, so subscribe if you're not with us, click the bell, and don't forget to give this video a like. Let's do this. The more there is, the faster the sequel will come out. Finally, a quasar is an object, not a phenomenon. The name quasar refers to a star-shaped source of radio waves. The explanation for this fact is very simple. Quasars were first discovered in the radio band. Currently, only 1% of quasars have detected appreciable energy emission in the form of radio waves. It is now common to see the term stellar objects. For a lover of astronomy, perhaps there is nothing more beautiful and mysterious than the starry sky. Suffice it to remember that these sparks in the night sky are actually huge balls of gas and plasma, the real size and properties of which are amazing. Although each star is unique and original in its own way, there are some record-breaking stars among them that break stereotypes with their performances. Size, weight, brightness. This is one of those record-breaking objects that we want to talk about today. Blue hypergiant R136A1.
Astrophysicists have assigned this beauty to the Wolf-Ray type, which suggests that it is characterized by the highest temperature and luminosity, since it is in the late stages of development. This is the most massive star in the universe known to science. First of all, if this star is now a record holder among its peers, how did it happen? The first way a star of this class is formed is by so-called natural birth. According to some scientists, the only thing that distinguishes this process from the classical process is the mass of the star at the time of its formation. On average, the mass of most stars at birth was equal to 150 solar masses. Another possibility is a gravitational merger of smaller stars. The evidence in favor of this opinion is the finding of blue giants in old clusters among red and yellow luminaries. It is from this fact that the theory was born that the remnants of old stars, or whole stars, merge into larger objects under the influence of their own gravity. Even with only red stars, which have a mass between 70 and 80% of the solar mass, a blue star can be born. Both ways in general sound quite logical, while soberly assessing at this stage which of them is the most realistic is quite difficult. The star R136A1 is not visible to the naked eye, but if you have a telescope with a 50-fold magnification like the famous Hubble, at the addressed dwarf galaxy of the Large Magellanic Cloud, Tarantula Nebula. Star cluster R136 can be seen the object of our interest. The distance between our Earth and this star is at least about 165,000 light-years. Here is an even more detailed address of a mysterious woman of colossal proportions. The Tarantula Nebula is located near the constellation Dorado, making it difficult to detect. It is very sad because the list of interesting objects is not limited to R136A1. Such objects include WOHG 64, a cool red supergiant, the largest star in the observable universe. But back to our blue hypergiant. At the same time, according to various estimates, it is quite young. Its age is about 2 million years, which is not surprising for stars of this type. But let's discuss the physical properties of the star, because they are of serious interest to scientists around the world. The little blue dot in the sky actually has amazing properties. The star's size, its radius of about 25 million kilometers, allows R136A1 to be classified as a hypergiant. That word sounds like the name of a comic book superhero from the early part of the last century, so let's simplify it a bit. Imagine our sun as we saw it in textbooks about the motherland. Now, let's create another sun nearby. Color it blue, which indicates a very high temperature. I want to remind you, and we'll gradually add to it, until 36 of our suns are included in the resulting megasphere. And that's just fast. But that's not enough. Now we begin to press the resulting ball until its mass reaches 315 solar masses. The picture is huge, and if you take it in tons, you get an unrealistic, I would even say inadequate number. That number makes R136A1 not only massive, but the most massive star ever found in the universe. After your imagination has tackled this really difficult task, you now have a rough idea of what this starfish looks like. But the image isn't ready yet. Add to that the volume indicator. It's 22,000 times more than our systemically important company. Now let's turn to a consequence of its colossal mass: temperature. This number reaches an incredible 55,000 Kelvin, and that's just the surface. This indicator exceeds solar energy by a factor of almost 10, and such a process as hydrogen combustion, which continues inside the star to this day, causes the core of R136A1 to heat up to several hundred million Kelvin. Mind you, what is left for us to finalize and finally visualize this point in the starry sky, indistinguishable to the naked eye? Actors, of course. R136. A1 is saturated with heavy elements, with carbon, nitrogen, and oxygen leading the way. Because of this, hydrogen-based nuclear fusion continues inside the star. This true stellar record breaker seemed to appear in all its glory. But that's not all. We have completely forgotten about such an indicator as brightness. And we are interested in this point not in the last place, because it is thanks to the luminosity of the star guilty, in quotes, in the creation of 10% of the ion fluxes of the entire Tarantula Nebula. And when it comes to the radiation from the star cluster, the numbers are even higher, 50%. So, if we equate our hypergiant to a chandelier and an ordinary-sized star to a lantern on a garland, then, in order to compensate for the glow of one such giant blue chandelier, a garland of at least 70 lanterns would be needed. Our sun, whose light spreads far enough to call it a luminary at all, emits less energy in a year than R136A1 does in 5 seconds.
It should be noted that such an indicator as total brightness is determined both by the light spectra visible to ordinary eyes and by invisible ranges of radiation. We are referring to the balometric absolute magnitude. In order not to scare us too much with calculations and figures, I will say that R136A1 is more than 8 million times brighter than the Sun. Of course, two interesting questions arise after these remarkable chapters. Is life possible under such conditions? And to what extent is it even possible? Could there be an exoplanet around this hypergiant? Judging by the size of the giant star, the habitable zone, a place where it's not too hot and not too cold, would be somewhere around 2950 AU, away from us. Recall that 1 astronomical unit is the average distance between the Earth and the Sun. Now imagine where in this blue hypergiant system our planet could be located. How much does it cost? But in general, the main indicator here is still the already mentioned brightness. The numbers are just symbols on paper, but it's actually much more complicated than that. Even if the sun's radiation intensity increased by 10%, life would remain only at the poles. An intensity of 40% turns Earth into another Venus. And now imagine what the radiation of R136A1 star, more powerful than the sun, can theoretically do to any exoplanet and even to the life that originated on it in a fraction of a second. That's right, memories. And we haven't even mentioned that 99% of this star's brightness comes from ultraviolet and X-rays. This composition is due to its temperature, which causes the wavelength of light to become very short, so short that the light goes beyond the visible range. For us at that moment, the effect is the same, the pale blue hue of a hypergiant. But on top of all this, a strong stellar wind is blowing, causing the star to rapidly lose matter. Otherwise, the future of star R136A1 is unfortunately predetermined. It's destined to go supernova, though not in the near future. The phenomena that astrophysicists call hypernovae were first observed in the early 1990s. The term itself had to be introduced because the explosive power of a hypergiant star exceeds the classical supernova explosion by at least a factor of 10, and it is accompanied by even longer gamma-ray bursts. Are such phenomena a threat? Absolutely yes, because according to some reports, gamma rays caused the Ordovician-Silurian extinction 440 million years ago, which resulted in the extinction of 0.6 vertebrates from Earth. Fortunately, it is not threatened by anything, as R136A1 is too far away. The blue hypergiant was discovered thanks to Hubble and the Very Large Telescope. Both megadevices were produced at the end of the last century. Today, scientists are ready to introduce new technologies that surpass existing ones. And there, who knows, maybe in the depths of space, we'll find even bigger stars expanding the classification. Well, right now, a blue hypergiant in the Large Magellanic Cloud galaxy, codenamed R136A1, is winning the Massive Star in the Universe category. There are many amazingly beautiful, yet terribly dangerous objects and phenomena in the universe. They include supernova explosions, the creation of colorful nebulae and pulsars spinning at incredible speeds. Here, and entire galaxies containing, among other things, the above objects. All of them have one thing in common. They are sources of gamma rays, deadly to all life. Gamma rays or gamma rays are a type of electromagnetic wave. For the nucleus of an atomic chemical element to emit gamma particles, it must be in an excited state, meaning energy must first be transferred to it, and then, when it becomes normal, it emits a stream of photons. Gamma particles emitted by their sources collide with matter at tremendous speeds, penetrate it, and begin to interact with its atoms and molecules, changing them. Radiant energy is transferred to atoms and molecules of matter, after which they become charged particles, ions.
It is very difficult to protect oneself from gamma rays. It has tremendous penetrating power, literally penetrating a person through and through. Simple clothing, medical masks or gloves are not enough to protect against it. Only very dense materials through which gamma rays cannot pass are suitable for shielding. A lead wall several tens of centimeters thick, or a concrete wall several meters thick. Some of these rays are produced by short-lived events such as solar flares or supernova explosions. But there are others, much more powerful, with a stable source. Black hole. At the center of most galaxies, including our Milky Way, is the nucleus, a compact but very massive object, a black hole. Their mass corresponds to tens of millions or even billions of solar masses. In the initial stages of evolution, a supermassive black hole absorbs surrounding matter, forming an accretion disk. When charged particles approach a black hole, they accelerate and collide, resulting in intense light emission. Such a black hole also has a strong magnetic field, which further rotates the falling particles and concentrates them in thin beams, jets that fly out from the poles. Their light is so bright that its brightness is comparable to trillions of suns, and of course, the power of such rays is simply enormous. If such a beam passes at a distance of at least 10 light-years from Earth, there is no more life in it. These jets are called quasars or blazars. Okay, wait a minute. Many of our viewers know what a quasar is. But what is a blazar? It's essentially the same thing as a quasar, or rather, a subclass of quasars, of course, with some differences. Let's talk about them in more detail. In general, the exact representation depends on the point of view. For example, if we see a jet perpendicular to our beam of vision, we see a radio galaxy. If the jet is tilted, we see a quasar. And finally, if it's pointed directly at us, it's a blazar. So when a supermassive black hole is the active nucleus of a galaxy, it can be called a quasar, a blazar, or a radio galaxy. It turns out, depending on what angle it is, turned to us. The first blazar found was originally misidentified as an irregular variable star. In 1929, the German astronomer Kuno Hofmeister published a catalog of 354 objects that he considered to be variable stars. That is, stars that change their brightness over fairly short periods of time. Included in this catalog was an object called BL lizards. In the late 1960s, astronomers began to notice that this object was getting brighter and dimmer, but not in a completely predictable way, and seemed to be emitting a lot of light in the radio wave mode, which was not typical of stars. Further investigation showed that BL Lizard was too far away to be considered a star in the Milky Way galaxy. And in some ways, its behavior resembled another mysterious object that astronomers had previously discovered: quasars, not variable stars. Astronomers eventually discovered that the BL spot was actually a bright object at the center of a distant galaxy. Other objects with the unique characteristics of the BL lizard became available for observation and are called BL Lac objects. Until 1980, astronomers suggested the name blazar from a combination of the words quasar and the variable BL Lac. There's also Lacertida, also from the original bill lizard. The thing is, in English, that's what you see on the screen right now, hence the name. Today, Lacertids, along with some quasars, are categorized as blazars. Studies in the 1980s and 1990s showed that the bright radio light of blazars comes from jets of material traveling at relativistic speeds. In the mid-1990s, astronomers determined that blazars, quasars, and some other bright galactic phenomena they observed belonged to the same family of objects: active galactic nuclei. Today, there are two models of blazars' manifestation.
The former includes radio quasars of equal frequency that show strong emission from an active accretion disk, much higher luminosity, smaller black hole masses, and lower particle acceleration in the ejected jets. Another model assumes blazars called Lacertids, where the emission from jets containing high-energy particles completely dominates, and the emission from the accretion disk is weak or absent. Blazars are characterized by a key feature: high variability in brightness. Unlike quasars, Lacertids do not have bright emission lines in their spectrum and are also characterized by radio emission. The Lacertids are most likely dormant quasars that have recognized readily available matter and have gone on a starvation diet. There are many more of them per unit volume than blazars, at least in the modern world, but they are only visible at low redshift. For example, object STA-102 is a redshift blazar, although Wikipedia for some reason calls it a quasar, whose light took about 7 billion years to reach us. As with all blazars, there is a complex, irregular variation in their emission, which is recorded in all ranges of electromagnetic waves, Most recently, this blazar had 2 flares in the fall of 2012 and in late 2016. It has increased its brightness tens or hundreds of times in a matter of weeks. The physical basis of the Blazarov variant is still debated. The basic model of these objects suggests that the matter in the blazar jets is ejected at velocities close to the speed of light, which explains its narrow angle emission and the high brightness of its luminosity. The emitting matter is not uniformly distributed along the jet, and in addition, different parts of the jet emit predominantly wavelengths of different wavelengths. The result is a highly variable source whose brightness in the radio and optical regions does not change synchronously, but with a slight shift in one direction or the other. However, there is a significant flaw in this explanation. The observed variability of STA-102 and its bright flares is difficult to explain without a complex model with a large number of parameters and subsequent fine physical tuning. The natural experience of testers suggests otherwise. The simpler the physical model, the more likely it is to match reality. Nature is lazy, though inventive. First, if the fluctuation of the blazar emission is geometric, then the amplitudes of its brightness or dimming should be the same at different wavelengths. We are looking at a source with a single emission spectrum, just from different angles at different times. Second, because of the effects of the same theory of relativity. Not only the brightness of the source changes, but also the time of its change, and therefore the change should be faster in the brighter state. By the way, that's the name of the brightest jacket in the sky. It really is a monster. During flares, it is much brighter than any other gamma-ray source. Its accretion disk emits in all regions about 10,000 times more energy than our entire galaxy. There are no direct measurements of the mass of a black hole, and they indicate a mass in the billions. If a black hole weighs 1 billion times more than the Sun, its gravitational radius is 3 billion kilometers. The radius of the accretion disk's last inner stable orbit is 10 billion kilometers, or 8 light hours. And the duration of this cycle is several days. This blazar is located 7.7 billion light-years away from us. That's a pretty close target for its type. Then the bright Quasars became extinct, and their golden age occurred more than 10 billion years ago. Thus, it is quite possible that in the future the light of the most distant blazars will reach us, and perhaps this will help us to study this cosmic phenomenon even better.